Tonight, we're going to explore something that seems straightforward, but turns out to be one of the most extraordinary concepts in all of science: the light year. You've likely heard this term countless times. Scientists mention it constantly when discussing the cosmos. But here's the part most people miss. When you genuinely understand what a light year means, when you truly comprehend the distance it represents, something shifts in how you perceive the universe. It's more than just a large number. It's a distance so immense that it pushes the boundaries of what our minds can grasp. Think about the words we use in everyday conversation. We say something is far away, and we think we understand what that means. But far is relative. Far to an ant is different from far to a bird, which is different from far to a human. And all of these are infinitesimally small compared to what far means in cosmic terms. The light year forces us to reconsider what distance actually means, to expand our mental framework beyond anything we've evolved to comprehend. By the time we finish this journey together, you'll understand exactly why astronomers depend on this measurement and why no other unit would make sense. Before we continue, if this kind of thoughtful exploration speaks to you, a quick like or subscribe really does help the channel. It's a small gesture for you, but it creates a meaningful difference for me. Now, let's begin. Let's start with something close to home: distance. You already understand distance in your everyday world. You know how far it is to the market, to your office, to the neighboring town. These are distances that feel real to you because you've experienced them. You have an intuitive sense of what they mean in terms of time, in terms of energy, in terms of what you'll encounter along the way. When you walk to the corner store, you know instinctively how long it will take. Your body understands the effort required. Your mind calculates whether you need to bring an umbrella, whether you should wear a coat, whether you have time before dinner. This is human-scale distance. It's written into our biology, encoded in our genes through millions of years of evolution. Our ancestors needed to know these distances to survive. How far to the waterhole? How far to safe shelter? How far they could travel before nightfall? A kilometre is roughly the distance you can walk in 10 to 12 minutes at a comfortable pace. These measurements serve us perfectly well for daily life. When someone mentions the store is 5 kilometers away, you know approximately how long the drive will take. You can imagine the journey in your mind. Perhaps you'll pass a handful of traffic signals. Perhaps you'll notice some familiar sights. The distance feels tangible and understandable. You might even know exactly which streets you'll take, which corners you'll turn, where you might encounter traffic. The journey exists in your mind before you take it because you understand the scale. 5 kilometers is about 3 miles. It's a distance a reasonably fit person could jog in 30 minutes or walk in an hour. It's the kind of distance that feels manageable, achievable, within the realm of normal human activity. When someone says a city lies 200 kilometers away, you can organize your trip accordingly. That's roughly 2 hours on the road. You'll want to check your fuel level, maybe pack some provisions. Consider a break along the way. These distances are scaled to human experience. They fit naturally into our lives and our understanding. We've evolved to comprehend distances we can cover in a day, distances we can observe, distances that matter for survival and finding our way. Our ancestors, walking across landscapes thousands of years ago, developed an intuitive understanding of these scales. They knew how far they could travel with the food and water they carried. They understood the relationship between distance and time, between effort and reward. They could look at a mountain on the horizon and estimate how many days of walking it would take to reach it. This understanding was essential for survival. Those who couldn't judge distances well, who underestimated how far the next water source was, or overestimated how much ground they could cover, didn't survive long enough to pass on their genes. But these measurements begin to feel clumsy when we discuss truly large distances. The distance from New York to Los Angeles spans roughly 4,500 kilometers. That's still a manageable number. It's about a 5-hour flight. People complete that journey regularly. They cross the continent. They watch the landscape transform from eastern cities to central plains to mountain ranges to southwestern deserts and finally to the western coast. The journey is substantial, but it's achievable. It's within human reach. You can picture yourself making that trip. Imagine making that journey by car. You'd drive for days, crossing time zones, watching the scenery change dramatically. You'd see the Appalachian Mountains give way to the flat expanses of Ohio and Indiana. You'd cross the Mississippi River, that great dividing line of the American continent. You'd traverse the Great Plains, where the land stretches flat to the horizon in every direction. You'd climb into the Rocky Mountains, ascending to heights where the air grows thin and snow caps the peaks, even in summer. You'd descend into the deserts of Nevada and Utah, where the landscape turns red and ancient. Finally, you'd crest the Sierra Nevada and descend into California, eventually reaching the Pacific Ocean. This journey, spanning the width of an entire continent, is still within human comprehension. People make it all the time. In pioneer days, it took months and was fraught with danger. Today, you can fly it in the time it takes to watch 2 movies. But whether by covered wagon or by airplane, it's a journey humans can complete, a distance we can understand. The Earth's circumference at the equator measures roughly 40,075 kilometers. That's a considerable number, but it's still something we can grasp conceptually. Early explorers sailed around the world, so we know it's possible to travel that distance, even if it requires months. Ferdinand Magellan's expedition took 3 years to circle the globe, from 1519 to 1522. Modern commercial flights can circle the Earth in about 45 hours if you could arrange connecting flights that travelled all the way around. Think about that accomplishment for a moment. In 1519, when Magellan's ships departed from Spain, most people believed the Earth was much smaller than it actually is. Some still weren't entirely convinced it was round. The journey was considered so dangerous, so impossible, that it was essentially a suicide mission. Of the 5 ships that departed with 270 men, only 1 ship returned with 18 survivors. Magellan himself died in the Philippines, never completing the journey he started. But they did it. They proved it was possible to sail all the way around the world, to travel that immense distance and return to where you started. It took 3 years of unimaginable hardship, starvation, disease, storms, and violence. But the Earth was circumnavigable. It was a finite distance that humans could traverse. Today, that same journey can be completed in less than 2 days of actual flight time. Commercial jets travel at roughly 900 kilometers per hour at cruising altitude. At that speed, you could circle the Earth at the equator in about 45 hours of continuous flight. Of course, no such flight exists because you'd need to refuel multiple times, but theoretically, it's achievable within 2 days. The Earth seems vast from our perspective, standing on its surface, but it's not beyond comprehension. It's a finite thing you could theoretically explore completely. Someone with enough time and resources could visit every continent, cross every ocean, climb every major mountain range. The Earth is large, but it's knowable, it's mappable. We have, in fact, mapped every square kilometre of its surface. Satellites have photographed the entire planet. There are no more blank spaces on the map, no more regions marked "Here be dragons." But now let's expand our scale. The distance from Earth to the Moon measures roughly 384,000 kilometers. This is where conventional measurements begin to feel insufficient. 384,000 kilometers. That's difficult to picture in any meaningful way. It's nothing like driving across a continent. It's nothing like sailing around the world. It's something entirely different. There's no road to follow, no reference points to pass, no places to stop along the way. It's simply distance, pure distance across empty space. To put this in perspective, you could fit 30 Earths in a line between Earth and the Moon. 30 entire planets, each with all their oceans and continents and mountains and cities lined up side by side, would just barely span the distance from here to the Moon. That's the first step in understanding cosmic distance. The Moon, which looks so close that you feel you could reach up and touch it, is actually 30 Earth diameters away. If you could somehow build a highway from Earth to the Moon and drive at a constant speed of 100 kilometers per hour, never stopping for food or sleep or fuel, it would take you 160 days to arrive. That's over 5 months of continuous driving. Imagine spending 5 months in your car, never stopping, just driving in a straight line through empty space. That's the distance to our nearest neighbor. How would you even begin to travel that far? The Apollo astronauts required approximately 3 days to journey from Earth to the Moon using powerful rockets that accelerated them to speeds around 11 kilometers per second. That's roughly 39,600 kilometers per hour, approximately 400 times faster than highway driving. Consider that for a moment, 400 times faster than you've ever driven. And even at that remarkable speed, which demanded some of the most powerful rockets ever constructed, consuming enormous quantities of fuel, it still required 3 days. 3 days of travelling through empty space at speeds no human had ever reached before, just to arrive at our closest celestial neighbour. The Saturn V rocket that launched the Apollo missions was, and remains, one of the most powerful machines ever built by humans. It stood taller than a 30-story building and weighed 6.5 million pounds when fully fueled. Most of that weight was fuel. The first stage alone burned through 2,000 tons of fuel in just 2.5 minutes, producing 7.6 million pounds of thrust. That enormous power was required just to escape Earth's gravity and begin the journey to the Moon. The astronauts sitting atop this controlled explosion experienced forces up to 4 times normal gravity during launch. The roar was so loud it could be heard over 80 kilometers away. The ground shook for miles around the launch site, and all of this tremendous power, all of this fuel, all of this engineering was required to cross a distance that's merely the first tiny step into space. And that's merely to the Moon, the nearest celestial body to Earth. The Moon is so close, you can observe it with your naked eyes. You can distinguish details on its surface with a simple pair of binoculars. It's right there, suspended in the sky. And yet, it demands 3 days of rocket travel to reach it. The Moon is so close that astronauts could see Earth in the sky above them when they landed. They could see the blue and white sphere of home hanging in the black lunar sky, looking fragile and small. From the Moon, you can watch Earth rotate. You can see the continents drift by as the planet turns. You can watch weather systems swirl across the oceans. It's right there. And yet, it's 3 days of rocket travel away, separated by a void that humans had never crossed until 1969. When we begin discussing the distance to other planets, to the Sun, to other stars, kilometers become entirely inadequate. The numbers grow so enormous that they lose all meaning. They transform into abstract symbols on a page rather than distances you can relate to in any way. The distance from Earth to the Sun spans roughly 150 million kilometers. Try to imagine that. You cannot, can you? Your mind simply registers it as an extraordinarily large number, but you lack any intuitive sense of what it represents. Nothing in your daily existence prepares you for a distance like that. 150 million kilometers. Let's try to make that more concrete, though ultimately we'll fail because our brains simply weren't designed to comprehend such distances. If you could stack Earths in a line from here to the Sun, you'd need almost 12,000 Earths, 12,000 planets, each roughly 13,000 kilometers in diameter, stretched in a line from Earth to the Sunday. If light from your flashlight could somehow reach the Sun, it would take 8 minutes and 20 seconds to get there. Light, traveling at 300,000 kilometers per second, still requires over 8 minutes to cross the distance from the Sun to Earth. That's how vast that space is. Nothing in human evolution equipped us to think about distances this vast. We evolved to understand the distance to the nearest water source, the distance to the hunting grounds, the distance we could travel in a day. We did not evolve to comprehend 150 million kilometers. The Apollo spacecraft that carried astronauts to the moon traveled at roughly 11 kilometers per second on average. At that speed, it would require about 160 days, over 5 months, to reach the Sun's distance. And remember, this is the spacecraft that got humans to the moon in 3 days. This represents some of the fastest speeds humans have ever achieved. And even at these speeds, crossing the distance to the Sun would require nearly half a year of continuous travel. You'd launch in winter and arrive in summer. You'd pass through 2 entire seasons just traveling in a straight line through space. The fastest spacecraft humans have ever constructed, the Parker Solar Probe, travels at speeds reaching 192 kilometers per second when it approaches the Sun, using its gravity to accelerate itself to higher and higher velocities. Even at this incredible speed, which is roughly 17 times faster than the Apollo spacecraft, the probe still requires months to complete its orbits around the Sunday. The Parker Solar Probe is a remarkable achievement of engineering. Launched in 2018, it's designed to study the Sun's outer atmosphere by flying closer to our star than any previous spacecraft. To survive the intense heat, it's protected by a special heat shield made of carbon composite foam, 12 centimeters thick. This shield can withstand temperatures of nearly 1,400 degrees Celsius on the sun-facing side, while keeping the instruments behind it at a comfortable room temperature. To reach its incredible speeds, the probe doesn't simply fly straight toward the Sunday. Instead, it uses a complex series of gravity assists from Venus, swinging past the planet multiple times to gradually increase its velocity and modify its orbit. Each pass brings it closer to the Sun and faster through space. It's a beautiful example of orbital mechanics, using the gravity of one celestial body to help reach another. And the Sun is close. It's right here in our cosmic neighborhood. It's the star we orbit. It's the source of all the light and warmth that makes life on Earth possible. We see it every day. It's familiar, and yet it's 150 million kilometers away, a distance so immense that even our fastest spacecraft requires months to traverse it. The Sun is our neighbor. It's in our backyard, cosmically speaking. It's the center of our solar system, the gravitational anchor that holds our planet in its orbit. 8 planets circle it, along with countless asteroids, comets, and smaller bodies. It's the defining feature of our local cosmic environment. And even at this relatively close distance, it might as well be infinitely far away by human standards. Every photon of sunlight that touches your skin has been traveling for 8 minutes and 20 seconds to reach you. The warmth you feel on a sunny day is energy that left the Sun's surface over 8 minutes ago. If you could somehow see the Sun in real time, if you could observe it as it actually is right now, you'd be seeing 8 minutes into its future, compared to what you see in the sky. That's how vast the distance is, even to our closest star. When we begin discussing distances to other stars, even the Sun's distance becomes tiny by comparison. The Sun is our nearest star, and it's 150 million kilometers away. The next nearest star, Proxima Centauri, sits roughly 266,000 times farther than that. 266,000 times farther than a distance that already takes our fastest spacecraft months to cover. Let that sink in for a moment. Take the distance from Earth to the Sun, a distance so vast that our fastest spacecraft needs months to cover it, and multiply it by 266,000. That's how far away the next nearest star is. It's not twice as far, it's not 10 times as far, it's 266,000 times as far. If the Sun were the size of a grapefruit sitting on a table in front of you, Earth would be a grain of sand orbiting about 15 meters away. At this scale, Proxima Centauri, the next nearest star, would be another grapefruit almost 4,000 kilometers away. That's the distance from New York to London. 2 grapefruits separated by an entire ocean representing the 2 nearest stars. And the space between them is almost entirely empty. No planets, no asteroids, no dust, just emptiness. This is why astronomers needed a different unit of measurement. Not because they enjoy making things complex, not because they want to perplex people with enormous numbers, but because kilometers simply fail when you're measuring cosmic distances. Using kilometers to measure distances to stars would be like using millimeters to measure the distance between nations. Technically feasible, but completely impractical. The numbers become so vast they lose all meaning. They stop being distances and become merely numbers. Abstract mathematical concepts that don't connect to anything in our experience. Imagine trying to give someone directions using millimeters. Turn left in 200 million millimeters, then continue for 1 billion millimeters. It would be absurd. Nobody thinks in millimeters for large distances because the numbers become unwieldy and meaningless. The same is true for using kilometers to measure cosmic distances. When you start talking about distances like 40 trillion kilometers, the number becomes so large it might as well be infinity for all the meaning it conveys to a human mind. So, astronomers developed something different, the light year. But here's what you need to grasp right from the beginning. A light year is not a measure of time. I know it contains the word year, which makes it sound temporal, but it's not. A light year is a measure of distance. It's the distance that light travels in 1 year. This confusion is understandable. We're used to years measuring time. I haven't seen you in years. This building is 100 years old. I'll finish this project in a year. Time is what we associate with years. But in astronomy, a light year is purely about distance. It's about how far light can travel in the span of 1 year. Think of it like this. If I told you marathon distance, you'd think of a specific distance, about 42 kilometers, even though the word refers to an event that takes time to complete. The light year works the same way. It's defined by light's journey through time, but it measures the distance covered, not the time taken. Now, why base a measurement on light? Because light is special. Light is the fastest thing in the universe. Nothing can travel faster than light. It's not simply a speed limit we haven't surpassed yet. It's a fundamental law of physics. The speed of light is constant, unchanging, identical everywhere in the universe. Whether you're on Earth, on Mars, in another galaxy, or at the edge of the observable universe, light always travels at the same speed, approximately 299,792 kilometers per second. This constancy is remarkable and counterintuitive. In our everyday experience, speeds are relative. If you're driving at 100 kilometers per hour and someone passes you driving at 120 kilometers per hour, they appear to be moving at only 20 kilometers per hour relative to you. If you throw a ball forward from a moving car, the ball's speed relative to the ground is your speed plus the ball's speed. Velocities add up in ways that make intuitive sense to us, but light doesn't work that way. Light always travels at the same speed relative to any observer, regardless of how fast that observer is moving. If you're standing still and measure the speed of a passing light beam, you get approximately 300,000 kilometers per second. If you're traveling at 99% the speed of light and measure the speed of a passing light beam, you still get approximately 300,000 kilometers per second. The speed of light doesn't change based on your reference frame. It's always the same, always constant, always exactly the same value. This strange property of light is what led Einstein to develop his theory of special relativity. If light speed is constant for all observers, then other things must change. Time must pass at different rates for observers moving at different speeds. Space itself must contract in the direction of motion. These bizarre consequences arise directly from the constancy of light speed. That's the speed limit of the universe itself. Nothing with mass can reach this speed, and nothing at all can exceed it. Light travels at this speed through the vacuum of space. At this velocity, light can circle the Earth's equator roughly 7.5 times in a single second. In 1 second, light can travel from New York to Los Angeles and back almost 20 times. These speeds are so far beyond human experience that they're nearly impossible to comprehend. But light has this speed, and it maintains this speed constantly. Imagine if you could travel at the speed of light. In 1 second, you could leave Earth, circle it 7.5 times, and be back where you started. In that same second, someone on Earth would have barely begun to register that you'd left. Their brain would still be processing the visual information of seeing you standing there, while you'd already completed 7.5 trips around the entire planet. In 1 minute at light speed, you could travel from Earth to the Sun and be halfway back. You could leave Earth, fly to our star, turn around, and be more than halfway home before a minute had elapsed on your watch. The distances we've been discussing, the vast emptiness between Earth and the Sun that takes our spacecraft months to cross, would become almost trivial at light speed. Of course, travelling at light speed is impossible for anything with mass. As objects approach light speed, strange things happen. Their mass effectively increases, requiring exponentially more energy to continue accelerating. Time dilation occurs, where time passes more slowly for the travelling object compared to stationary observers. The object also contracts in length in its direction of motion. These aren't just theoretical predictions. They're observed effects that we've measured in particle accelerators and with high-speed particles from space. So when we say a light year, we're talking about the distance light travels in 1 year. Let's calculate that distance. Light travels at roughly 300,000 kilometers per second. That's a useful approximation. In 1 second, light covers 300,000 kilometers. In 1 minute, that's 60 seconds. Light travels 18 million kilometers. In 1 hour, that's 60 minutes. Light travels 1 billion to 80 million kilometers. In 1 day, that's 24 hours. Light travels roughly 25 billion and 920 million kilometers. In 1 year, that's 365 days. Light travels approximately 9.46 trillion kilometers. Let's break this calculation down step by step. because each stage is worth contemplating. In 1 second, light travels 300,000 kilometers. That's roughly the distance from Earth to the Moon in just over 1 second. The journey that took Apollo astronauts 3 days, light completes in a heartbeat. In 1 minute, 60 of those seconds, light travels 18 million kilometers. That's about 12% of the distance from Earth to the Sunday. In the time it takes you to boil water for tea, light could travel 12% of the way to our star. In 1 hour, light travels over 1 billion kilometers. That's enough to travel from the Sun to beyond the orbit of Saturn. The entire inner solar system, from the Sun out past Jupiter, could be crossed by light in about an hour. In 1 day, light travels nearly 26 billion kilometers. That would take you beyond the orbit of Pluto and well into the outer solar system. All the planets, from Mercury to Neptune, all their moons, all the asteroids and comets, the entire classical solar system, exists within the distance light can travel in about 5.5 hours. 9,460 billion kilometers. That's 1 light year. Let's pause there for a moment, because that number needs time to settle. 9.46 trillion kilometers. Written out, that's 9 followed by 12 zeros. It's a number so large that it's essentially meaningless to our everyday understanding. There's nothing in human experience that prepares us to comprehend a distance like that. You can't visualize a trillion of anything, let alone a trillion kilometers. If you started counting to 1 trillion, counting one number per second, 24 hours a day, never sleeping, never stopping, it would take you almost 32,000 years to reach 1 trillion, longer than all of recorded human history. And that's just counting to 1 trillion, not actually traveling 1 trillion kilometers, which would be vastly more difficult. If you could drive a car at highway speed around the clock, never stopping for fuel or maintenance, it would take you over 10 million years to drive 1 light year. 10 million years is longer than humans have existed as a species. Modern Homo sapiens have only been around for about 300,000 years. A light year is so vast that driving it would take 30 times longer than our entire species has existed. But this is what astronomers use as a basic unit for measuring cosmic distances. This is their kilometer, their mile, their fundamental measure of space. And the reason they use it, the reason they need it, is because the distances in space are so incomprehensibly vast that even this enormous unit, 9.46 trillion kilometers, becomes a convenient way to express them. When astronomers say a star is 20 light years away, they're using this enormous unit as if it were commonplace. They're saying that star is 20 of these incomprehensible distances away. But in cosmic terms, 20 light years is actually quite close. It's our immediate neighborhood, our closest stellar neighbors. The Milky Way galaxy, our home galaxy, is roughly 100,000 light years in diameter. That means light, traveling at its incredible speed, would take 100,000 years to cross from one side of our galaxy to the other. 100,000 years. Agriculture has only existed for about 10,000 years. Human civilization as we know it didn't exist 100,000 years ago. And yet, that's how long light would take to cross our single galaxy. And the Milky Way is just one galaxy among trillions. The nearest major galaxy, Andromeda, is 2.5 million light years away. The distances between galaxies dwarf the distances between stars, which themselves dwarf the distances between planets, which themselves dwarf any distance we can comprehend through everyday experience. It's scales within scales within scales, each level making the previous one seem insignificant. Remember that distance to our Sun? 150 million kilometers? That seems enormous. It is enormous by human standards, but in light years, it's tiny. The Sun sits approximately 8 light minutes away from Earth. Not 8 light years, 8 light minutes. The light from the Sun takes 8 minutes to reach us. That means when you look at the Sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. The light that's entering your eyes left the Sun 8 minutes in the past. Think about what that means. If the Sun suddenly vanished, disappeared from existence, we wouldn't know for 8 minutes. We'd continue to see it shining in the sky, continue to feel its warmth, for 8 full minutes after it was gone. The light that was already on its way, already travelling through space toward us, would continue arriving for those 8 minutes. Only after that delay would the Sun disappear from our sky, would its warmth cease to reach us. Of course, the gravitational effects would also take 8 minutes to reach us. Gravity, like light, propagates at the speed of light. So if the Sun vanished, Earth would continue orbiting the empty point where the Sun used to be for 8 minutes before flying off in a straight line. For those 8 minutes, we'd be orbiting a Sun that no longer existed, held by gravitational waves that had left the Sun before it disappeared. This delay, this light travel time, is the fundamental reality of cosmic observation. We never see anything as it is now. We always see things as they were when the light we're observing left them. For nearby objects, this delay is negligible. For distant objects, it becomes profound. If the Sun suddenly changed colour, started pulsing, or did anything unusual, we wouldn't see it happen for 8 minutes. Astronomers studying the Sun are always viewing events that happened 8 minutes ago. They're studying the past, not the present. This is always true in astronomy, but becomes more dramatic as distances increase. That's how long light takes to cross the distance from the Sun to Earth. Now let's talk about other stars. Proxima Centauri, the nearest star to our Sun, sits approximately 4.24 light years away. That means the light we see from Proxima Centauri tonight left that star 4.24 years ago. When you look at Proxima Centauri in the night sky, if you could see it with your naked eye, which you cannot because it's too dim, you would be seeing light that left that star over 4 years ago. If intelligent beings lived on a planet orbiting Proxima Centauri and they looked at our Sun, they would see it as it was over 4 years ago. They would be seeing Earth's past, viewing events that have already happened here. If we sent a radio signal to Proxima Centauri, it would take 4.24 years to arrive. If someone there immediately sent a response, it would take another 4.24 years to come back. So the absolute minimum time for any exchange of information with our nearest stellar neighbour would be 8.5 years. You could ask a question and receive an answer almost a decade later. The person who sent the question might have changed jobs, moved to a different city, gotten married, or had children in the time it took to get a response. If you could somehow travel at the speed of light, which is impossible for anything with mass, it would still take you 4.24 years to reach Proxima Centauri. But we can't travel at the speed of light. Our fastest spacecraft, the Parker Solar Probe, at its maximum speed, travels at roughly 0.064% the speed of light. At that speed, it would take roughly 66,000 years to reach Proxima Centauri. 66,000 years. Let's put that in historical perspective. 66,000 years ago, modern humans were just beginning to spread out of Africa into Europe and Asia. They were hunter-gatherers living in small bands, using stone tools and fire. They had language and art, but no agriculture, no cities, no writing, no metal tools. They were anatomically modern humans. but their society would be utterly unrecognizable to us. In the 66,000 years since then, humanity has gone from small nomadic tribes to a global civilization of nearly 8 billion people. We've invented agriculture, writing, mathematics, science, cities, nations, and civilizations. We've gone from stone tools to spacecraft, from cave paintings to computers, from campfires to nuclear reactors. The entirety of everything we consider human civilization has happened in the time it would take our fastest spacecraft to reach the nearest star. 66,000 years is longer than all of recorded history multiplied by 13. The Great Pyramids of Egypt, among the oldest structures still standing, were built only about 4,600 years ago. The entire span from their construction to the present day represents less than 7% of the time it would take to reach Proxima Centauri at our current maximum spacecraft velocity. If we launched a mission to Proxima Centauri today with our current technology, assuming we could maintain that speed for the entire journey and the spacecraft didn't break down, it would arrive in the year 68,025. By that time, human civilization will have changed so dramatically that we can't even begin to imagine what it will look like. Our languages will have evolved beyond recognition. Our nations will have risen and fallen multiple times. The very shape of human society will be completely different, and the spacecraft would just be arriving. 66,000 years. Human civilization as we know it has only existed for about 10,000 years. Written language has only existed for about 5,000 years. The entire span of recorded human history would fit into the journey to our nearest stellar neighbour with room to spare. The oldest written records we have, cuneiform tablets from ancient Mesopotamia, date back about 5,000 years. Everything we know about history, every war, every empire, every invention, every great work of art and literature, all of it has happened in the most recent 5,000 years of human existence. And that entire span represents less than 8% of the time it would take to reach Proxima Centauri. Think about what this means for space exploration. We dream about traveling to the stars, about exploring other solar systems, about finding new worlds, and perhaps even meeting other civilizations. But the distances make it almost impossibly difficult. Even our nearest neighbour is so far away that reaching it would take longer than human civilization has existed. And that's just to the nearest star. Most stars you can see in the night sky are much farther away. Sirius, the brightest star in our night sky, sits 8.6 light years distant. The light you see from Sirius tonight began its journey 8.6 years ago. Sirius, that brilliant blue-white star that catches your eye on winter evenings, is one of our close neighbours at 8.6 light years. But even that relatively close distance translates to about 81 trillion kilometres. At our fastest spacecraft speed, reaching Sirius would take roughly 100 to 34,000 years. That's twice as long as it would take to reach Proxima Centauri. Imagine launching a mission to Sirius. The spacecraft leaves Earth, perhaps from a launch pad in Florida or Kazakhstan. News anchors announce the historic mission. People gather to watch the launch. Children look up in wonder, but none of those children will live to see the spacecraft arrive. Neither will their children nor their children's children. Thousands of generations would live and die before arrival. The mission planners who designed the spacecraft will be dead. The engineers who built it will be dead. The civilization that launched it might not even exist anymore in recognizable form. Languages will have changed. Technology will have advanced. The Earth itself will have changed. Climate shifts, geological events, evolution itself will continue, while that spacecraft crawls through the void towards Sirius. Vega, another bright star, is 25 light years away. Betelgeuse, the red supergiant in Orion's shoulder, lies roughly 550 light-years distant. The light you see from Betelgeuse tonight left that star 550 years ago. It departed Betelgeuse in the 1400s during the Renaissance, before Columbus sailed to the Americas. That light has been travelling through space for over 5 centuries to reach your eyes tonight. In 1474, when the light now reaching us from Betelgeuse began its journey, Leonardo da Vinci was 22 years old and just beginning his career as an artist. Michelangelo was not yet born. The printing press had been invented only about 20 years earlier, and books were still rare and precious. The Americas were unknown to Europeans. The Protestant Reformation hadn't happened. The scientific revolution hadn't begun. The modern world didn't exist yet. That light has been travelling through the vast emptiness of space for all the centuries since. It travelled while Columbus crossed the Atlantic, while the Renaissance flourished, while the age of exploration circled the globe, while the scientific revolution transformed human understanding, while the Industrial Revolution mechanized society, while 2 world wars reshaped civilization, while humans landed on the moon, while the internet connected the world. Through all of that human history, that light has been travelling toward Earth, and tonight it reaches your eye. A photon that left Betelgeuse 550 years ago, carrying information about what that star looked like back then, completes its journey by striking your retina. In that moment, you're directly connected to the past. You're seeing history, not in a book or a photograph, but directly, immediately, through light that has bridged the centuries. Betelgeuse might not even look like that anymore. It's a red supergiant, a massive star near the end of its life. Astronomers expect it to explode as a supernova sometime in the next 100,000 years. It might have already exploded. The star might have detonated 50 years ago, 100 years ago, 500 years ago. But we wouldn't know because the light from that explosion is still travelling toward us. We're still seeing Betelgeuse as it was 550 years ago, frozen in time by the finite speed of light. When Betelgeuse does explode, whenever that happens, it will be spectacular. A supernova at that distance will be bright enough to see during the day, bright enough to cast shadows at night, bright enough to be visible even in brightly lit cities. It will appear as a brilliant new star in the sky, blazing steadily for weeks or months before gradually fading. Ancient cultures would have interpreted it as a sign or omen. We'll understand it as the death throes of a massive star. And these are relatively nearby stars, our neighbours in cosmic terms. When we look at more distant objects, the numbers become even more staggering. The centre of our Milky Way galaxy sits roughly 26,000 light-years away. When you look toward the centre of our galaxy, you're seeing light that began its journey 26,000 years ago during the last ice age, when humans were still hunter-gatherers and hadn't yet invented agriculture. 26,000 years ago, Earth was a very different place. Massive ice sheets covered much of North America and Europe. Sea levels were over 100 meters lower than today because so much water was locked up in glaciers. You could walk from Asia to North America across a land bridge where the Bering Strait is now. Mammoths, saber-toothed cats, giant ground sloths, and other megafauna roamed the landscape. Humans existed, but in very different circumstances. We were nomadic hunter-gatherers, following animal herds and seasonal plant resources. We had language, art, and culture, but no agriculture, no permanent settlements, no cities. The total human population was probably less than 5 million people worldwide, compared to nearly 8 billion today. Everything that has happened since then, all of human civilization, from the agricultural revolution to the present day, has occurred while light from the centre of our galaxy was travelling toward us. That light left the galactic center while humans were still painting on cave walls, while we were just beginning to develop more sophisticated tools and social structures. It has been traveling through space for the entirety of human civilization and more. The Andromeda Galaxy, our nearest large galactic neighbor, rests 2.5 million light-years distant. The light you can see from Andromeda on a dark night started its journey 2.5 million years ago, back when our ancestors were early hominids, just beginning to use stone tools. The light has been traveling since then, crossing the vast emptiness of intergalactic space to finally arrive at Earth and enter your eyes tonight. 2.5 million years ago, our ancestors were Australopithecus and early Homo species, creatures that walked upright and used simple stone tools, but had brains much smaller than modern humans. They looked different from us, thought differently, lived differently. They were our ancestors, but they would seem alien to us in many ways. The genus Homo, which includes modern humans, had just appeared or was about to appear. The evolutionary journey from those early hominids to modern humans, encompassing countless generations, dramatic brain expansion, the development of language, art, complex tools, and eventually culture and civilization. All of that has happened while light from Andromeda was traveling toward us. When you look at Andromeda on a dark autumn night, seeing that faint smudge of light that is actually a galaxy of 1 trillion stars, you're seeing it as it was before humans existed in any recognizable form. You're looking at history on an evolutionary timescale. The galaxy has changed since then. Stars have been born and died. Planets have formed. Perhaps civilizations have risen and fallen. But we see none of that. We see only the ancient light that has finally completed its long journey to Earth. When we look at distant galaxies through powerful telescopes, we're looking billions of light years into space, which means we're also looking billions of years back in time. The most distant galaxies we've observed sit over 13 billion light years away. The light from these galaxies began its journey over 13 billion years ago, not long after the Big Bang itself, when the universe was young and very different from what it is today. The universe is 13.8 billion years old. The most distant galaxies we observe date from when the universe was only a few 100 million years old. These galaxies formed from the first generation of stars made almost entirely of hydrogen and helium because heavier elements hadn't been created yet. These stars were massive, bright, and short-lived, living only millions of years before exploding as supernovae and scattering heavier elements into space. The galaxies themselves looked different back then. They were smaller, more irregular, more chaotic. The neat spiral and elliptical galaxies we see in our cosmic neighborhood today had not yet formed. The early universe was a wilder, more violent place, with galaxies colliding and merging more frequently, with star formation rates much higher than today, with black holes actively consuming matter and blazing as quasars. These galaxies might not even exist anymore in their current form. They might have collided with other galaxies, been torn apart by gravity, evolved into something completely different. We have no way of knowing what they look like right now, because right now is 13 billion years away from us. We can only see them as they were 13 billion years ago. This is one of the most profound aspects of astronomy. The deeper we look into space, the further back in time we see. Distance and time become intertwined in cosmic observation. Every observation is also a historical record. The universe has a built-in history book, preserved in the light that has been traveling toward us from distant sources. Imagine if we could somehow see galaxies as they are right now, 13 billion years after the light we're observing left them. They would look completely different. Some might have been destroyed in galactic collisions. Some might have evolved into massive elliptical galaxies. Some might be in the process of merging with neighbors. But we can't see any of that. We can only see the past, preserved in light. This is what makes astronomy so strange and so beautiful. When you look up at the night sky, you're not seeing the universe as it is. You're seeing the universe as it was. You're looking backwards through time. Every star, every galaxy, every point of light is showing you its past, not its present. The farther away something is, the farther back in time you're looking. The moon, you see as it was 1.3 seconds ago. The sun, as it was 8 minutes ago. Jupiter, as it was about 40 minutes ago, when it's at its closest to Earth. Saturn, as it was about an hour and 20 minutes ago. Neptune, our most distant planet, as it was about 4 hours ago. Each object in our solar system is showing you its past, though the delay is small enough that it doesn't matter much for most purposes. But for stars and galaxies, the delays become profound. Proxima Centauri, as it was 4.24 years ago. Sirius, as it was 8.6 years ago. Vega, as it was 25 years ago. Betelgeuse, as it was 550 years ago. The night sky becomes a historical panorama with different objects showing you different eras of cosmic history. Astronomy is time travel of a sort. We can't travel forward or backward in time ourselves, but we can observe the past directly by looking at distant objects. The light from those objects carries information about what they were like when that light was emitted, sometimes billions of years ago. This is how we study the early universe, how we understand what galaxies looked like in their youth, how we piece together cosmic history. We're not guessing or speculating. We're observing directly, watching ancient light arrive after its long journey through space. Every telescope is a time machine. The Hubble Space Telescope, orbiting Earth since 1990, has observed galaxies from the early universe, looking back in time nearly to the Big Bang. The James Webb Space Telescope, launched in 2021, can see even further, observing some of the first galaxies that formed after the cosmic dark ages, when the universe was filled with neutral hydrogen that blocked most light. These observations give us a direct window into cosmic history. We can see how galaxies evolved over time by comparing nearby galaxies, which show us recent cosmic history, with distant galaxies, which show us ancient history. We can watch the universe age, see how it has changed over billions of years, understand the processes that shaped it into what we observe today. This is how we know the universe is expanding. By measuring the distances to galaxies and their motion, we discovered that more distant galaxies are moving away from us faster. The entire universe is expanding, with galaxies moving apart from each other as space itself expands. We can trace this expansion backward in time, determining that the universe was once much smaller, much denser, much hotter. Eventually, tracing far enough back, we reach the Big Bang, the beginning of space and time as we know it. Now let's talk about what light years mean for space exploration, for our dreams of traveling to other stars, for the possibility of finding other civilizations in the universe. These are profound questions that touch on our future as a species, and light years are at the heart of all of them. Remember that Proxima Centauri, our nearest star, sits 4.24 light years away. And remember that at our current fastest spacecraft speeds, it would take roughly 66,000 years to reach it. That's a timescale that's difficult to comprehend. It's longer than all of recorded history. It's longer than human civilization has existed in its current form. If we launched a spacecraft to Proxima Centauri today using our best current technology, it wouldn't arrive until the year 68,025. Assuming it could somehow maintain its speed for the entire journey, the people who launched it would be dead. Their children would be dead. their children's children would be dead. Countless generations would live and die before the spacecraft arrived. This presents a fundamental challenge for interstellar exploration. How do you plan a mission that will outlast civilizations? How do you maintain continuity of purpose across timescales that dwarf all of human experience? Who would fund such a mission, knowing that not just they, but their entire civilization in its current form would be gone before any results came back? The engineers who designed the spacecraft would never see it arrive. The scientists who planned the mission would never analyze any data from the destination. The civilization that built and launched the spacecraft would have changed so dramatically that the people living when it arrived might not even care about its mission anymore. Their priorities would be different. Their technology would be different. They might not even remember why their ancestors launched it. And that's just to the nearest star. Most stars are much farther. To reach a star 50 light years away would take roughly 780,000 years at current speeds. To reach a star 100 light years away would take 1.5 million years. These timescales are so vast, they make space exploration seem almost futile. 780,000 years ago, modern humans didn't exist yet. Our ancestors were early members of the genus Homo, probably Homo heidelbergensis, living in Africa and parts of Europe and Asia. They had stone tools and fire, but their brains were smaller than ours, their culture simpler. They weren't us yet. The entire evolution from those ancestors to modern humans has taken less time than it would take to reach a star 50 light years away at our current spacecraft speeds. How do you plan a mission that will take thousands or millions of years? How do you build something that can survive that long? How do you maintain purpose and continuity across timescales that dwarf all of human history? This is the challenge that light years present to space exploration. The universe is not just large. It's large in a way that makes it almost impossible to explore using conventional means. Even if we could build faster spacecraft, the problem remains. To get anywhere interesting in space, you need to travel significant fractions of the speed of light, and that's incredibly difficult. As objects with mass approach the speed of light, strange things happen. Their mass effectively increases, requiring more and more energy to accelerate them further. Time dilation occurs, where time passes differently for the travelers compared to people back on Earth. The amount of energy required becomes astronomical, far beyond anything we can currently produce. Let's explore these challenges more deeply. Accelerating even a small spacecraft to a significant fraction of light speed requires enormous amounts of energy. The kinetic energy of a moving object increases with the square of its velocity. Double the speed, quadruple the energy. Triple the speed, 9 times the energy. This relationship holds at everyday speeds. But as you approach light speed, things get worse, much worse. The energy required increases exponentially, approaching infinity as you approach light speed. To accelerate a 1-ton spacecraft to 90% the speed of light would require energy equivalent to the entire annual energy production of current human civilization. For a larger spacecraft, multiply that energy requirement accordingly. And that's just to accelerate the spacecraft. You'd also need to decelerate it at the destination, requiring the same amount of energy again. And if you wanted the spacecraft to return, you'd need to accelerate and decelerate twice more. The total energy required quickly becomes absurd, far beyond anything we can produce or even imagine producing. Let's imagine, just as a thought experiment, that we could build a spacecraft that travels at 10% the speed of light. That's already an enormous achievement, far beyond our current capabilities. At 10% light speed, it would take 42 years to reach Proxima Centauri. That's within a human lifetime, barely. You could launch a mission with young astronauts, and some of them might survive to see arrival. 42 years. That's a long time. but it's manageable on human timescales. People have devoted their entire careers to single projects. Some research programs last 40 years. Some telescopes and space missions operate for decades. A 42-year journey to another star system, while unprecedented, would at least be something humans could conceptually handle. An astronaut who launched at age 25 would be 67 at arrival. Old, but not impossibly so. They would have spent their entire adult life aboard the spacecraft, traveling through the void. They might have had children during the journey, children who were born in space and grew up knowing only the interior of the spacecraft. Those children might be the ones who actually explored the new system while their parents were too old. The psychological challenges would be enormous. Spending decades in a confined space, knowing you can never return home, watching Earth recede to a point of light and then vanish entirely. The crew would need to maintain their mental health, their sense of purpose, their relationships with each other. They would need systems to handle conflict, depression, boredom. They would need activities to keep themselves occupied during the long voyage. But even at this speed, which would require technological breakthroughs we can't yet imagine, reaching more distant stars would take centuries. A star 50 light-years away would require 500 years of travel. A star 100 light-years away would require 1,000 years. 500 years. That's back to the time of Columbus, back to the Renaissance. Imagine a ship that launched in 1524 and was scheduled to arrive today. The people who launched it would seem like aliens to us. They spoke older versions of modern languages. They had completely different worldviews. They understood the world in ways that seem quaint or bizarre to us now. And yet, if such a ship existed, it would only now be completing its journey. We'd be back to generation ships, spacecraft that would travel for so long that the people who arrived would be distant descendants of the people who launched. The crew who arrived would have been born aboard the spacecraft. They would have no memory of Earth except what they'd been taught. Their entire lives would have been spent in transit. Earth would be a myth to them, a story their ancestors told, a place they'd seen only in videos and pictures but never visited. Or we'd need to develop some kind of suspended animation, putting the crew to sleep for centuries. This is a common science fiction solution, but the reality is far more challenging. How do you keep a human body viable for hundreds of years? How do you protect against cosmic radiation during that time? How do you ensure the life support systems keep functioning? What if there's a malfunction and no one is awake to fix it? Or we'd need to become functionally immortal, extending human lifespan to thousands of years. This is perhaps the most ambitious option. If humans could live for thousands of years, interstellar travel becomes more feasible. You could launch on a journey knowing you'd survive to see the end. But achieving such longevity would require radical advances in biology and medicine. Breakthroughs we can't currently envision. Each option presents its own incredible challenges. This is the tyranny of the light year. This is why, even though we can see stars scattered across the sky, even though we can study them and understand them, we may never reach them. The distances are simply too vast. The speed of light is simply too slow when measured against cosmic scales, and we can't travel at the speed of light anyway. There's another implication of these vast distances that's worth considering. If intelligent life exists elsewhere in the universe, and statistically it seems likely that it does, we may be fundamentally isolated from each other by the light years that separate us. Communication, even if we could establish it, would be agonizingly slow. A radio signal sent to Proxima Centauri would take 4.24 years to arrive. A reply would take another 4.24 years to return. That's 8.5 years for a single exchange of messages. To have a conversation would be impossible. Imagine trying to communicate this way. You send a message. Hello, We are humans from Earth. We've detected your signal and would like to establish contact. Then you wait. 4.25 years pass. You go about your life. You have birthdays. You change jobs. Perhaps you have children. Meanwhile, your message is traveling through space at the speed of light, crossing the vast distance to Proxima Centauri. Finally, it arrives. The recipients, whoever or whatever they are, receive your message. They spend some time discussing it, deciding how to respond, composing a reply. Then they send it back. Another 4.25 years pass, while their response travels to Earth. Over 8 years after you sent your original message, you receive a reply. More than 8 years of your life have passed. The world has changed. Technology has advanced. The political situation is different. You're older, and you've received a single message in reply to your single message. This is the fundamental challenge of interstellar communication. To have anything resembling a conversation would require patience on timescales that test human limits. Each exchange would take years. A simple question and answer session would span decades. Any complex negotiation or discussion would require centuries. And that's with our nearest stellar neighbour. For more distant stars, the delays become even more prohibitive. A signal to a star 50 light years away would take 50 years to arrive and 50 years for the reply. A century for one exchange. Think about that. You could send a message as a young adult and receive a reply as an elderly person. Your entire career, your entire adult life, would pass between sending a message and receiving a response. The people who sent the message might be retired or dead by the time the reply arrived. A signal to a star 100 light years away would require 2 centuries for a round trip. The people who sent the original message would be dead. Their children would be dead. Their grandchildren might be approaching the end of their lives. The generation that received the reply would be the great-great-great-great-grandchildren of those who sent the message. They would be inheriting a conversation that their ancestors started, continuing a dialogue that began before they were born. These are timescales longer than human lifetimes, longer than nations typically exist, longer than most civilizations maintain continuity of purpose. We might send a message and receive a reply generations later, from people who had inherited the communication from their ancestors, replying to a civilization that had changed beyond recognition. The Roman Empire lasted, in its Western form, about 500 years. In its Eastern form, as Byzantium, it lasted another 1,000 years. But even that remarkable longevity would barely suffice for interstellar communication with distant stars. A conversation with a civilization 500 light years away would take 1,000 years for each exchange. The Roman Empire could have sent a message at its founding and received a reply just as it was collapsing, if it had maintained that purpose for its entire existence. This is the isolation that light years create. We can see the stars, we can study them, we can know they exist, but we may never reach them, never communicate with them in any meaningful way, never bridge the vast distances that separate us. We're like islands in a vast ocean, able to see each other from a distance, but unable to make contact across the empty space between. This is both frustrating and humbling. Frustrating because the universe is filled with places we might never reach, with potential civilizations we might never contact, with questions we might never answer. But humbling because it reminds us that the universe is vast beyond our ability to fully explore it, that we are small and limited, that there are fundamental constraints built into the nature of reality itself. Some people find this depressing. The idea that we might be forever confined to our tiny corner of the universe, unable to explore the cosmos beyond our immediate neighborhood, unable to meet other civilizations if they exist. But there's another way to look at it. Consider what we have accomplished. We're creatures who evolved on a single planet. descendants of organisms that first emerged in Earth's oceans billions of years ago. We evolved to survive in our local environment, to find food and water, to avoid predators, to reproduce. Nothing in our evolutionary history prepared us to understand the cosmos. Our ancestors were fish, swimming in ancient seas. Before that, they were simple multicellular organisms, barely differentiated from single-celled life. Before that, they were single cells, microscopic specks floating in the ocean, and before that, they were just molecules, complex chemistry emerging from simpler compounds. Nothing in that long evolutionary history, stretching back billions of years through countless forms of life, prepared us to understand the universe. Evolution shaped us to survive, to reproduce, to pass our genes to the next generation. It shaped our senses to detect food and predators. It shaped our minds to navigate our local environment, to remember where resources were, to predict the behavior of other organisms. But somewhere along the way, something remarkable happened. Our brains, evolved for survival, became capable of abstract thought. We developed the ability to think about things beyond our immediate experience. We could imagine scenarios that hadn't happened. We could plan for the future. We could understand cause and effect. And eventually, we could contemplate the nature of reality itself. And yet, we do understand it, at least in part. We've figured out that we live on a planet orbiting a star. We've determined the distances to other stars, measured in light years. We've observed galaxies billions of light years away. We've pieced together the history of the universe, from the Big Bang to the present. We've discovered fundamental laws of physics that govern everything from the smallest subatomic particles to the largest structures in the cosmos. We've determined that the universe is 13.8 billion years old. We've calculated its size, measured its expansion rate, understood its composition. We know it's made mostly of dark matter and dark energy, mysterious components we can't directly observe, but whose effects we can measure. We know how stars form, how they evolve, how they die. We know how planets form from the debris left over from star formation. We know how galaxies evolve, how they collide and merge, how they organize into larger structures. We figured out the age of the Earth, 4.5 billion years. We've understood how life arose from non-living chemistry. We've traced the evolution of life from simple cells to the vast diversity of species we see today. We've understood our own evolutionary history, how we're related to all other life on Earth, how we emerged from ancestral primates. We've done all of this using our brains. Organs that evolved to help us survive on the African savanna, now turned toward understanding the universe itself. We've built instruments that extend our senses far beyond their natural limits. Telescopes that can see light that's been traveling for billions of years. Detectors that can sense radiation invisible to our eyes. Computers that can process data and perform calculations far beyond human capability. The most powerful telescopes can observe galaxies so distant that the light has been traveling since the early universe. They can detect faint signals that left their sources billions of years ago. They can analyze that light, breaking it into its component wavelengths, determining what elements are present in distant stars, how fast those stars are moving, whether they're approaching or receding from us. We've built spacecraft that have visited every planet in our solar system. We've landed probes on Mars, Venus, Titan. We've flown past Pluto and beyond. We've sent spacecraft into interstellar space, beyond the sun's influence, carrying messages intended for any intelligent beings that might find them. We've built particle accelerators that recreate conditions from the early universe, allowing us to study physics at energies that haven't existed naturally since shortly after the Big Bang. We've detected gravitational waves, ripples in space-time itself, created by colliding black holes billions of light years away. We've photographed a black hole's event horizon, imaging an object so dense that not even light can escape it. We've developed mathematical frameworks that can describe the behavior of objects moving at nearly the speed of light, the curvature of space-time around massive objects, the quantum behavior of particles. We've created a body of knowledge that allows us to understand, at least conceptually, things we can never directly experience. Quantum mechanics describes the behavior of particles so small we can never observe them directly. Relativity describes the behavior of objects moving so fast or in gravitational fields so strong that we can never directly experience those conditions. Yet we can understand these things mathematically, predict their behavior, test our predictions through experiments. That's extraordinary. That's something to be proud of. We may never travel to other stars, but we can understand them. We can measure their properties, determine their composition, track their life cycles. We can know what they're made of, how they formed, how they'll eventually die. We know that stars are powered by nuclear fusion, converting hydrogen into helium and releasing energy. We know that more massive stars fuse heavier elements, creating carbon, oxygen, silicon, iron. We know that when massive stars die, they explode as supernovae, scattering these heavy elements into space. We know that new stars and planets form from this enriched material, incorporating these elements. We know that our own sun is a second or third generation star, formed from material that was processed through previous generations of stars. The heavy elements in our solar system, including the ones in our bodies, were created in stars that died before the sun was born. We are, quite literally, made of stardust. We may never visit other galaxies, but we can observe them, catalogue them, study their structure and evolution. We can watch them collide and merge. We can see new stars being born in their spiral arms. We can detect the black holes at their centers. We've observed thousands of galaxies, understanding how they're distributed in space, how they cluster together into groups and superclusters, how these structures trace out vast cosmic webs of matter. We've seen galaxies of all types, spiral galaxies, like our own, elliptical galaxies, irregular galaxies, dwarf galaxies. We've watched galaxies collide in slow motion, observing multiple stages of galactic mergers by looking at different galaxies at different distances. This knowledge, this understanding, is its own form of exploration. We're exploring the universe intellectually, even if we can't explore it physically. We're bridging the light years with observation and analysis and mathematics. We're reaching across vast distances using the light that travels from distant objects to our instruments. In a sense, every time you look up at the night sky and understand what you're seeing, you're participating in this exploration. You're receiving light that has travelled across light years to reach you. Photons that left distant stars years or centuries or millennia ago are entering your eyes right now, completing journeys that began long before you were born. You're connected to those distant stars across space and time by the light that bridges the gap between you. This connection is real and physical. Every photon that enters your eye from a distant star has travelled across light years of space specifically to reach you at this moment. It's been travelling for years or centuries, maintaining its direction, carrying its information, crossing vast emptiness. And at this precise moment, it completes its journey by interacting with molecules in your retina, triggering a cascade of chemical reactions that your brain interprets as light. You are the destination for those photons. In a universe of unimaginable vastness, these photons crossed enormous distances to arrive at the specific location where your eye happened to be at this specific moment. That's remarkable when you think about it. You're catching light from the distant past, light that has been traveling since before you were born. This is what makes astronomy so profound. It's not just abstract science. It's a direct connection to the cosmos. When you observe a star, you're not just seeing light. You're receiving information that traveled across light years specifically to reach you. You're the destination for photons that have crossed vast emptiness to arrive at this precise moment. The information carried by those photons tells you about the star's temperature, its composition, its motion, its age. All of this encoded in the wavelengths and intensities of light. Astronomers can analyze this light, breaking it into a spectrum, identifying which wavelengths are present and which are absorbed. From this, they can determine what elements are present in the star, how hot it is, whether it's moving toward or away from us, and much more. There's something almost spiritual about that, though it's grounded entirely in physics. The universe is vast beyond comprehension, but you're part of it. You're made of atoms that were forged in stars that died billions of years ago. Their matter scattered across space and was eventually incorporated into new stars and planets, and ultimately into you. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces and distributed through supernovae. Think about the journey of a single calcium atom in your body. It was created inside a massive star billions of years ago, forged in the intense heat and pressure of stellar fusion. When that star exhausted its fuel, it exploded as a supernova, scattering that calcium atom across space along with countless other atoms. The atom drifted through space for millions or billions of years, eventually becoming part of a cloud of gas and dust that collapsed to form our solar system. It might have been part of asteroids or comets first, before eventually becoming incorporated into Earth during the planet's formation or through later impacts. On Earth, it cycled through rocks and minerals, perhaps dissolved in the ocean, incorporated into marine organisms, deposited in sediments, uplifted into mountains, weathered and eroded. Eventually, through some pathway involving plants and animals and food chains, it ended up in your body, in your bones, helping give them strength and structure. And one day, after you die, that atom will be released again, continuing its cosmic journey, perhaps eventually being incorporated into another organism, another structure. It's immortal, in a sense, this atom, cycling through the universe on a journey that began in a star and will continue long after you're gone. You're not separate from the cosmos. You're part of it. You're a way the universe has developed to know itself, to observe itself, to understand its own nature and history. That's what Carl Sagan meant when he said, "We are a way for the cosmos to know itself." We're not outside observers looking at the universe. We're part of the universe, a part that has become conscious and curious. The universe is 13.8 billion years old. For most of that time, it was just matter and energy, following physical laws, evolving but not knowing itself. Stars formed and died. Galaxies evolved. The universe expanded. But there was no consciousness, no awareness, no entity capable of observing and understanding what was happening. Then, on at least one small planet orbiting an ordinary star, something remarkable occurred. Life emerged. Simple at first, just chemistry, becoming complex enough to reproduce itself. But over billions of years, that life evolved, became more complex, developed sensory systems, nervous systems, eventually brains capable of modeling the world. And finally, at least in one species on this one planet, consciousness emerged. Self-awareness, the ability not just to experience the world, but to think about that experience, to wonder why, to ask questions, to seek understanding. The universe became aware of itself through us. Understanding light years, Understanding the vast distances they represent gives us perspective on our place in the cosmos. When you look up at the stars and realize they're light years away, when you understand that the light entering your eyes began its journey years or centuries or millennia ago, it changes something. It reminds you that you're part of something immensely larger than yourself, that the universe existed long before you were born and will continue long after you're gone. That Earth is a tiny stage in an enormous cosmic arena. This perspective is called the overview effect. Astronauts who've seen Earth from space often describe a profound shift in their worldview. Seeing our planet as a small sphere floating in the blackness of space, seeing how thin and fragile our atmosphere appears, seeing continents and oceans and weather patterns from above, but no borders, no nations, no divisions, creates a deep understanding of our unity and vulnerability. Even without leaving Earth, understanding light years can create a similar shift. When you realize that everything human, all of history, all of civilization, all of our struggles and achievements has happened on a tiny planet orbiting an ordinary star in one galaxy among trillions, it provides perspective. Our problems seem smaller, our disagreements seem less important, our shared humanity becomes more apparent. But it also reminds you that you're here, now, able to observe and understand and appreciate all of this. That's remarkable. You could have existed at any point in the universe's history, but you exist now, at a time when humans have developed the tools and knowledge to understand light years and cosmic distances. You could have been born in any era of human history, but you were born in an era when we can observe galaxies billions of light years away, when we can study the early universe, when we can contemplate our place in the cosmos with actual knowledge rather than mythology. Our ancestors, for all of human history until very recently, looked up at the same stars we see. They wondered about them, created stories about them, recognized patterns and constellations, used them for navigation and calendars. But they didn't know what stars actually were. They didn't know they were distant suns. They couldn't conceive of the distances involved. They had no way to measure cosmic scales. Only in the last few centuries have we begun to understand. Only in the last 100 years or so have we measured distances to other galaxies. Only in the last few decades have we understood the full scale of the universe. You live at a unique moment in human history when this understanding is new enough to be exciting but established enough to be reliable. That's a privilege. It's something our ancestors couldn't do, something our distant descendants will likely take for granted, but something that's new and wonderful for us right now. When you walk outside on a clear night and look up at the stars, you're seeing photons that have traveled across light years to reach you. You're looking back in time. You're witnessing the universe as it was years or centuries or millennia ago. On a truly dark night, away from city lights, you can see the Milky Way stretching across the sky like a river of light. That band of light is our view of our own galaxy from the inside, seeing countless stars at various distances, all combining to create that milky appearance. You're seeing your cosmic home, your galactic neighborhood, from a perspective that few humans in history have truly appreciated. That star you're looking at might not even exist anymore in its current form. It might have exploded as a supernova decades ago, but the light from that explosion hasn't reached us yet. We're still seeing the star as it was, frozen in time, preserved in the light that's still traveling toward us. Think about Betelgeuse, that red supergiant in Orion's shoulder. Betelgeuse is roughly 550 light years away. The light you see tonight left that star 550 years ago. Astronomers think Betelgeuse might explode as a supernova sometime in the next 100,000 years. It might have already happened. The star might have exploded 100 years ago, or 50 years ago, or 10 years ago, but we don't know yet because the light from that explosion hasn't reached us. We're still seeing Betelgeuse as it was 550 years ago, shining steadily in the sky. In late 2019 and early 2020, Betelgeuse underwent a dramatic dimming, dropping to about 40% of its normal brightness. Astronomers wondered if this might signal an imminent supernova. The media reported on the possibility. People looked up at Orion, wondering if they were witnessing the final days of this ancient star. But the dimming turned out to be caused by a massive dust cloud that the star had ejected, temporarily blocking our view of its surface. Betelgeuse brightened again, returning to normal. The supernova, whenever it happens, was not imminent. But the episode reminded us that we're watching stars at a delay. When Betelgeuse does explode, that explosion might have occurred centuries ago. The light is still traveling toward us. If Betelgeuse has already exploded, we won't know until the light from the explosion arrives. When it does, it will be spectacular. A supernova at that distance would be visible during the daytime, bright enough to cast shadows at night, visible for months. It would be the astronomical event of our lifetime, probably of several lifetimes. Historically, bright supernovae have been recorded by various cultures. In 1054, Chinese astronomers recorded a guest star that appeared in the constellation Taurus and was visible during the day for 23 days. That supernova created the Crab Nebula, still expanding today. In 1572 and 1604, European astronomers observed supernovae, events that challenged the prevailing belief that the heavens were unchanging and perfect. A nearby supernova visible from Earth is rare. The last one that was easily visible to the naked eye was supernova 1987A, which occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. It was visible from the southern hemisphere and was intensively studied by astronomers worldwide. Before that, you'd have to go back to 1604 to find a supernova visible without telescopes. Betelgeuse's eventual explosion would be by far the brightest supernova in recorded human history. At about 550 light-years away, it's closer than any star that's gone supernova during human civilization. It would outshine the moon, be visible even in daytime, and remain bright for months or years. It would be a once-in-many-lifetimes event, a cosmic spectacle that would be remembered for generations. But if it has happened, the light is still travelling toward us, crossing the light years between Betelgeuse and Earth, carrying news of the explosion. And when it arrives, when we see Betelgeuse suddenly brighten and transform, we'll be seeing something that happened centuries ago, witnessing an event from the deep past finally becoming visible. This is the strange nature of cosmic observation. We're always looking at the past. We can never see the universe as it is right now. We can only see it as it was when the light we're observing began its journey. For nearby objects, the delay is small. The moon is about 1.3 light seconds away. When you look at the moon, you're seeing it as it was 1.3 seconds ago. That's negligible. The moon is so close, in cosmic terms, that the delay is essentially meaningless for most purposes. If an asteroid hit the moon, you'd see the flash 1.3 seconds after it happened. If astronauts were on the lunar surface and waved at Earth, we'd see them wave 1.3 seconds after they did it. For practical purposes, we can treat the moon as existing in the same now as us, even though there's technically a delay. The sun is 8 light minutes away. When you look at the sun, you're seeing it as it was 8 minutes ago, still recent enough that it doesn't matter much. But for distant stars and galaxies, the delay becomes significant. When you observe a galaxy a billion light years away, you're seeing it as it was a billion years ago. You're looking at ancient light, observing something from the deep cosmic past. 1 billion years is an enormous span of time. 1 billion years ago, life on Earth was simple, multicellular organisms. The most complex life forms were probably sponges and simple algae. There were no fish, no plants on land, no animals. Earth was a completely different planet. The continents were arranged differently. The atmosphere had less oxygen. It was an alien world compared to today. While all of that evolution was happening on Earth, light from a distant galaxy was traveling toward us. It crossed intergalactic space, traveling at the speed of light, but still taking 1 billion years to cover the distance. Every major development in the history of complex life on Earth occurred while that light was in transit. The Cambrian explosion, the colonization of land by plants and animals, the age of dinosaurs, their extinction, the rise of mammals, the evolution of humans, all of human history, all of civilization, all happened while that light was traveling toward Earth. And tonight, that photon completes its journey by entering a telescope, being detected by a sensor, analyzed by a computer, and eventually seen by a human eye. After a 1 billion-year journey, it has reached its destination. The galaxy might look completely different now, 1 billion years later. It might have collided with another galaxy, might have formed billions of new stars, might have exhausted its gas and stopped forming stars entirely. We have no way of knowing because the light showing us what it looks like now won't arrive for another 1 billion years. This is both frustrating and wonderful. Frustrating because we can never observe the universe as it currently is, because there's always a delay, always a gap between what we see and what exists. But wonderful because it means we can study cosmic history directly. We can observe how galaxies looked billions of years ago. We can watch the universe evolve over time by looking at objects at different distances, and therefore at different times in cosmic history. By observing galaxies at various distances, we're essentially looking at different pages in the universe's history book. Nearby galaxies show us what galaxies look like recently in cosmic terms. Galaxies a few billion light years away show us what galaxies look like in the Middle Ages of the universe. Very distant galaxies show us what galaxies look like in the universe's youth. Nearby galaxies show us what galaxies look like recently. Distant galaxies show us what galaxies looked like billions of years ago when the universe was younger. By comparing them, we can piece together how galaxies evolve, how they change over cosmic timescales. We can create a timeline of the universe, understanding how it developed from the Big Bang to the present, by observing objects at different distances and therefore different times. Astronomers have created surveys of galaxies at various distances, essentially sampling different epochs of cosmic history. They can see how galaxy shapes have changed over time, how star formation rates have evolved, how supermassive black holes have grown, how the large-scale structure of the universe has developed. It's like having snapshots from different eras of cosmic history, allowing us to piece together the full story. Light years make this possible. They give us a time machine of sorts. Not one we can travel in, but one we can observe through. Every light year of distance is also a year back in time. Look 50 light years away and you see 50 years into the past. Look 1 million light years away and you see 1 million years into the past. Look 13 billion light years away and you see 13 billion years into the past, nearly to the beginning of the universe itself. This is one of the most remarkable aspects of modern astronomy. We're not speculating about the early universe. We're not guessing what it was like. We're observing it directly. The light from those early epochs has been traveling toward us for billions of years, and it's arriving now, carrying information about what the universe was like back then. This is how we know what the early universe looked like. This is how we discovered that galaxies were smaller and denser billions of years ago. This is how we learn that the universe has been expanding for billions of years. We're watching cosmic history unfold, preserved in light that has been traveling toward us across incomprehensible distances for incomprehensible amounts of time. The expansion of the universe was discovered by observing that distant galaxies are moving away from us, and the more distant they are, the faster they're receding. This relationship, discovered by Edwin Hubble in the 1920s, implies that the universe is expanding, with space itself growing larger over time. Running this expansion backward, we can calculate when everything was compressed into a single point, giving us the age of the universe and strong evidence for the Big Bang. So what does all of this mean for us, for humanity, for our future? Understanding light years, understanding the vast distances they represent, changes our perspective in profound ways. It humbles us. It shows us that we're tiny, that Earth is a tiny planet orbiting an ordinary star in an ordinary galaxy, that the universe is unimaginably vast and we occupy an insignificantly small corner of it, that the distances between stars are so immense that we may never overcome them, never explore beyond our immediate cosmic neighborhood. We're confined, at least for now, to our solar system. We've visited our moon. We've sent robotic probes to all the planets. We've landed rovers on Mars, dropped probes into Jupiter's atmosphere, flown through the geysers of Enceladus, landed on comets and asteroids. But we haven't left the sun's domain. We haven't reached another star. We haven't truly entered interstellar space except with a few probes that will drift for tens of thousands of years before nearing another stellar system. Our entire species, all 8 billion of us, all of our history, all of our achievements, all of our conflicts, everything human has happened within one solar system, on one planet, orbiting one star. From a cosmic perspective, we haven't gone anywhere. We're still at home, still in our birthplace, still confined to our tiny island in the vast cosmic ocean. But it also elevates us. We've figured this out. We've measured these distances. We've understood our place in the universe, despite being confined to a single planet. We've developed the knowledge and tools to observe and comprehend things billions of light years away. We're conscious beings who can contemplate infinity, who can understand concepts that don't exist in our immediate experience, who can grasp truths about reality that evolution never prepared us for. This is the paradox of the human condition. We're simultaneously insignificant and extraordinary. Insignificant in scale, confined to a tiny planet for a brief moment in cosmic time, but extraordinary in consciousness, in our ability to understand, in our capacity to comprehend our own insignificance. No other species on Earth can do this. No other organism can look at the stars and understand what they're seeing. No other creature can contemplate the size of the universe, the age of the cosmos, the distance to the nearest star. This ability is unique to humans, at least on Earth. It might be unique in our region of space. We might be the only consciousness capable of such understanding within many light years. That's extraordinary. Consider this. You're standing on a planet that's 4.5 billion years old. You're made of atoms that are even older, that were created in stars that lived and died before the sun was born. You're part of a universe that's 13.8 billion years old, that contains trillions of galaxies, each with billions of stars. And you're able to understand this. You're able to comprehend the light year, to grasp what it means, to appreciate the vast distances it represents. The atoms in your body have been on a journey that predates the solar system. They were created in previous generations of stars, scattered when those stars died, drifted through space, eventually became part of the molecular cloud that collapsed to form the sun and its planets, ended up in Earth, cycled through rocks and water and atmosphere, were incorporated into living organisms, passed through food chains, and eventually ended up in you. Some of those atoms might have been part of dinosaurs, part of ancient ferns, part of the first fish to crawl onto land, part of the first cells to use oxygen, part of the primordial ocean. They've been on Earth for billions of years, cycling through countless forms, and now they're part of you, arranged in the specific configuration that makes you who you are. And these atoms, these ancient travelers, are now part of a conscious being that can contemplate their own origin, can understand where they came from, can grasp the vast scales of space and time that led to this moment. That's remarkable. You can look up at the night sky and know that you're seeing across light years. You can understand that the photons entering your eyes have travelled for years or centuries to reach you. You can appreciate that we live in a tiny corner of an enormous cosmos, on a small planet orbiting an ordinary star in one galaxy among trillions. When you stand outside on a clear night and look up at the stars, you're participating in something that humans have done for countless generations. Our ancestors looked up at the same stars, saw the same constellations, wondered about the same lights in the sky. But you have knowledge they lacked. You understand what those lights are. You know their distant suns. You know they're light years away. You can comprehend the vast distances involved in a way they never could. You're the beneficiary of centuries of scientific progress, of countless observations and calculations, of insights from brilliant minds who dedicated their lives to understanding the cosmos. You're standing on the shoulders of giants, seeing farther than they could because of the foundation they built. There's something profoundly humbling about understanding light years and the distances they represent. It reminds us how small we are in the grand scheme of things, how brief our individual lives are compared to cosmic timescales, how isolated we are in space, separated from even our nearest stellar neighbours by distances that would require thousands of years to cross with any technology we can currently build. It places our concerns and worries and problems into perspective, showing us that from a cosmic viewpoint, the things that seem so important in our daily lives are temporary and local. Your personal problems, your career concerns, your relationship difficulties, your financial worries, all of these things that can seem overwhelming in the moment become smaller when viewed against the backdrop of cosmic scales. This isn't to diminish the reality of human suffering or suggest that personal problems don't matter. They do matter, enormously, to the people experiencing them. But there's value in perspective. When you're stressed about a deadline at work, it can help to remember that Earth is a tiny planet orbiting an ordinary star, that everything human has happened here, that the stars you can see have been shining for millions or billions of years and will continue long after your deadline has passed. When you're caught up in political arguments, it can help to remember that we're all together on this small world, separated from our nearest stellar neighbours by light years, united by our shared humanity and our shared home. This perspective doesn't solve problems, but it can help us maintain balance, can remind us what's truly important, can help us see our challenges in a larger context. But there's also something empowering about this knowledge. We figured this out. Despite being small creatures on a small planet, we measured these vast distances. We understood our place in the universe. We built telescopes and spacecraft and developed mathematical frameworks that allowed us to see and comprehend things billions of light years away. We are tiny, confined to one small world for now, but we're also remarkably capable. We're conscious beings who can understand the universe that created us, who can look up at the night sky and comprehend what we're seeing, who can contemplate distances measured in trillions of kilometers and timescales measured in billions of years. We've done things that would seem like magic to our ancestors. We've split atoms and released energy. We've decoded the structure of DNA and understood the basis of heredity. We've developed quantum computers that use the properties of subatomic particles to perform calculations. We've created artificial intelligence that can beat humans at complex games and tasks. We've built a global communication network that allows anyone to access vast stores of information instantly. And we've measured the universe. We've determined distances to galaxies billions of light years away. We've calculated the age of the cosmos. We've understood the fundamental forces that govern reality. We've watched the evolution of the universe from the Big Bang to the present day. We're small, but we're mighty in our ability to understand. From a cosmic perspective, you're insignificant. Your life is a brief flicker, lasting perhaps 80 or 90 years if you're fortunate, in a universe that's 13.8 billion years old and will continue for trillions of years more. You exist for the blink of an eye on a tiny planet orbiting an ordinary star. The universe existed for 13.8 billion years before you were born. It will exist for trillions upon trillions of years after you die. The current best estimates suggest that the universe will continue expanding forever, gradually cooling and darkening, until eventually all the stars have burned out, all the black holes have evaporated, and nothing remains but a cold, dark, nearly empty space. That process will take so long that our current age, the age of stars and galaxies, will seem like a brief, bright moment in the universe's history. You exist during a special time, cosmically speaking. You exist during the age when stars are still shining, when galaxies are still forming new stars, when the universe is still relatively young and vibrant. In the far future, any conscious beings that exist will look out on a very different universe, one that's darker, colder, more spread out. They might not even be able to see distant galaxies, because the expansion of the universe will have carried them beyond the horizon of observable space. But you're also remarkable in your own way. You're made of atoms forged in the hearts of stars that died billions of years ago. Their matter scattered across space and eventually recycled into new stars and planets, and ultimately into you. You're literally made of stardust, the product of cosmic processes that have been operating for billions of years. You're a way for the universe to know itself, to understand itself, to appreciate its own vastness and beauty and complexity. Every atom heavier than hydrogen and helium in your body was created in a star. The oxygen you breathe, the carbon that forms the backbone of your biochemistry, the nitrogen in your DNA, the calcium in your bones, the iron in your blood, all of it was forged in stellar cores or in the explosive deaths of stars. You're not just in the universe, you're of the universe. You're made of the same stuff as the stars, organized in a particular way that creates consciousness. So the next time you look up at the stars on a clear night, remember what you've learned tonight. Those points of light scattered across the darkness are not just lights. They're distant suns, massive spheres of fusing hydrogen, each one potentially hosting its own system of planets and moons. They're light years away, separated from us by distances so vast that the light entering your eye right now, the photons that travelled across space to reach you, has been travelling for years or centuries. Some of that light began its journey before you were born. Some of it left its star before your grandparents were born. You're receiving ancient light that began its journey in the past and is only now completing it. You're connected to those distant stars across the vast distances of space and time, linked by light that has crossed the cosmic void to reach you. You're part of a process that has been occurring for billions of years, the journey of light from sources across the universe to destinations where it can finally be observed. You're connected to those distant stars across the vast distances of space and time, linked by light that has crossed the cosmic void to reach you. The universe is vast beyond comprehension. You are small, a a single person on a single planet. But you're here, and you can understand, at least conceptually, if not intuitively, what a light year really means. You can grasp that the universe is measured in these vast units. That space is filled with distances that dwarf anything in human experience. And that understanding, that ability to comprehend your place in the cosmos, is extraordinary. This understanding is recent in human history. For most of our existence as a species, we didn't know what stars were. We created myths and stories to explain them, imagined them as holes in the celestial sphere, or as gods, or as campfires in the sky. We couldn't conceive of the distances involved, had no framework for understanding cosmic scales. Only in recent centuries have we begun to truly understand. And you're part of the first generation that has grown up with this knowledge as established fact, that can learn about light years in school, that can see images from the Hubble telescope of distant galaxies. This is a privileged position in human history. It's what makes us human, what separates us from other life on Earth. We can look up and understand what we're seeing. We can contemplate infinity and our own smallness simultaneously. We can feel both humbled and empowered by the same knowledge. And perhaps that's the most important thing to take away from understanding light years. Not just the technical definition, not just the mathematics of 9.46 trillion kilometers, but what it means for us as a species, for our future, for our place in the cosmos. We stand at a unique moment in history. We're the first generation of humans to truly understand the scale of the universe. Throughout human history, various cultures have created different cosmologies, different models of the universe. Ancient Greeks imagined crystalline spheres carrying the planets. Medieval Europeans imagined a geocentric universe with Earth at the center. Many cultures imagined a relatively small, cozy universe made for humans. But now we know better. We know the universe is almost incomprehensibly vast. We know we're not at the center. We know we're on a small planet orbiting an ordinary star in an ordinary galaxy. This knowledge is new. It's only in the last century that we've really understood the scale of things, and we're still coming to terms with what it means. Our ancestors looked up at the same stars, wondered about the same questions, but they didn't have the tools or knowledge to measure the answers. They couldn't know that the stars were distant suns. They couldn't know that those suns were light years away. They couldn't comprehend the vast distances that separate us from the rest of the universe. They looked up with wonder and imagination, creating stories and myths to explain what they saw. The constellations are the result of this ancient human impulse to find patterns and meaning in the night sky. Different cultures saw different patterns, created different stories, but all humans throughout history have looked up and wondered. But we can. We've measured these distances. We've calculated them precisely. We know that Proxima Centauri is 4.24 light years away. We know that the Andromeda Galaxy is 2.5 million light years distant. We know that the observable universe stretches 93 billion light years across space. These aren't guesses or estimates. They're measurements backed by decades of careful observation and calculation. The methods for measuring these distances are ingenious. For nearby stars, we can use parallax, observing how their apparent position shifts as Earth orbits the Sun and using geometry to calculate their distance. For more distant objects, we use standard candles, objects whose intrinsic brightness we know, allowing us to determine their distance by measuring how bright they appear to us. For the most distant galaxies, we measure their redshift, how much their light has been stretched by the expansion of the universe. The more distant they are, the faster they're receding from us, and the more their light is redshifted toward longer wavelengths. By measuring this redshift, we can determine their distance. These methods have been refined over decades, tested against each other, verified through multiple independent techniques. The distances we quote are not speculative. They're the result of careful scientific work by thousands of astronomers over many decades. This knowledge changes us. It has to. When you truly understand that the nearest star would take thousands of years to reach with our current technology, when you grasp that the light from distant galaxies has been traveling for billions of years to reach your eyes, when you comprehend that we might be fundamentally isolated by the vast distances of space, it shifts your perspective on everything. It changes how you see your place in the universe. It changes what you value. It changes how you think about humanity's future. These aren't abstract changes. They're real shifts in worldview that occur when you truly internalize the scale of the cosmos. It makes our differences seem smaller. The things we argue about, the borders we draw, the conflicts we engage in, all of it happens on one tiny planet in a vast cosmos. We're all together on this small world, separated from our nearest stellar neighbours by distances measured in light years. From that perspective, the things that divide us seem less important than the things we share. When astronauts look back at Earth from space, they don't see borders. They see one integrated whole, one living planet, one shared home. The perspective of understanding light years and cosmic distances can create a similar shift even without leaving Earth. It can help us see our shared humanity, our common fate, our collective responsibility to this one small world we all share. The problems that seem so large and intractable, the conflicts that seem so important, the divisions that seem so fundamental, all of them shrink in significance when viewed against the backdrop of cosmic scales. This doesn't mean they don't matter, but it provides perspective, reminds us what's truly important. It also makes our existence seem more precious. If we're alone, or effectively alone because we can't reach anyone else across the light years that separate us, then what we do here matters enormously. We might be the only consciousness in our region of space, the only minds that can contemplate the universe and understand what they're seeing, the only beings who can create art, discover scientific truths, feel love and compassion and wonder. If we are alone, or at least alone in the sense that we can never contact anyone else due to the tyranny of distance, then we have a unique responsibility. We're the universe's only way of knowing itself, at least in this corner of space. If we destroy ourselves, if we fail to preserve what we've learned, if we don't take care of our planet, then this unique perspective might be lost, perhaps forever in this region of space. That's a profound responsibility. It means we need to take care of this planet, this tiny island of life in the cosmic ocean. It means we need to preserve and protect the knowledge we've gained, the understanding we've developed. It means we need to think long-term, not just about the next year or decade, but about the next century, the next millennium, the long future of humanity among the stars. We need to address climate change, preserve biodiversity, reduce inequality, prevent nuclear war, manage emerging technologies responsibly, not just for ourselves, but for the sake of consciousness itself. If we're the only conscious beings in our region of space, if we're the only entities capable of understanding the universe, then our survival and flourishing matters cosmically, not just personally or tribally or nationally. The light year is more than just a unit of measurement. It's a reminder of our place in the universe, a reminder that we're part of something vastly larger than ourselves, but also that we're unique and precious within that vastness. A reminder that the stars are both incredibly far away and intimately connected to us through the light that bridges the cosmic distances. Every time you look up at the night sky, you're participating in something ancient and profound. You're seeing across light years. You're looking back in time. You're witnessing the universe in all its majesty. And you're part of that universe. made of the same atoms, following the same physical laws, connected by the same fundamental forces that govern everything from the smallest particle to the largest galaxy cluster. You're participating in a ritual that humans have performed throughout our existence. Every culture, every civilization, every people throughout history has looked up at the night sky and wondered. You're continuing that ancient tradition, but with a crucial difference. You understand what you're seeing. You have knowledge that your ancestors lacked. You're part of the first generation that can look up not just with wonder, but with understanding. That's what a light year really means. Not just distance, but connection. Not just isolation, but belonging. Not just our smallness, but our significance within that smallness. Thank you for joining me on this journey through space and time. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me continue making these thoughtful explorations of the cosmos. And remember, even though light years represent distances almost beyond comprehension, they're also what connect us to the stars. Every time you look up at the night sky, you're seeing across light years. You're seeing the universe, and the universe, vast as it is yours to explore. Not necessarily physically, not by traveling in spacecraft across the void, but intellectually, through observation and understanding and wonder. You're part of something magnificent. You're made of stardust, living on a small world orbiting an ordinary star, conscious and capable of understanding your own cosmic context. That's extraordinary. That's worth celebrating. That's worth preserving. Good night, and may you never look at the stars the same way again.